Hey, good afternoon, everybody. Um, so let us welcome Shivam Garg for his talk in this colloquium today. And Shivam will be talking about quality of service aware routing protocols for airborne networks. So Shivam has been working on design of protocols and more specifically the MAC and routing layer protocols, which are layer 2 and 3 in the wireless networks, specifically targeting decentralized airborne networks. So airborne network, for those who are not much familiar, they are a class of ad hoc networks where the source and destination cannot talk to each other directly. So the data travels through intermediate nodes. Internet also does the same thing. Data passes through the gateways, but internet is much more structured. Here we are looking at the nodes which are mobile, and they join and leave dynamically. So when you establish a route or a path from source to destination, the route may break. So there are new protocols required. The existing protocols do not work well. So Shivam has worked on MAC layer protocol, which is how to access the channel and send the data. And now he's looking into routing layer protocols, and that's what he will talk about. So Shivam, over to you.
Thank you, Professor. Thank you for the introduction. And I would also like to thank Dr. Castillo for giving me the opportunity to present my work in front of you today. And thanks all for joining. Let me share my screen. I hope you are able to see this, right? So as Professor mentioned, today I'll be talking about QoS-Aware routing protocol for airborne wireless networks. And I want to acknowledge my advisors, Dr. Sunil Kumar and Dr. Alexander Eiler. And this project has been funded by US Air Force Research Laboratory. So in today's talk, I'll basically cover the introduction of airborne networks, the problem formulation, the progress we have made so far, and I'll conclude with the future work. So you might have already seen the applications of airborne networks, right? It has applications in civil space also, and in military space as well. So for example, commercial and goods delivery, urban coverage and surveillance, and disaster management, and military has their own applications. So what is airborne network? Airborne networks are they have high node density, and they are highly mobile. They are self-configurable, multi-hop, and decentralized. They must satisfy dynamic quality of service requirements of multiple flows. So there can be a lot of different source destination pairs. So that's what I mean by flows. And while doing that, it needs to take care of priority aware communication. It makes sure that the in-time delivery is satisfied, high flow throughput, there should be fault tolerance, and the energy efficient transmissions in order to increase the lifetime of the network. So in our work, we have considered a network of low size, weight, and power fixed wing UAVs. And since UAVs move at a high speed, they cannot make sharp turns. So this results in smooth trajectories. So this is one of the features which differentiates airborne networks from rest of the mobile ad hoc networks. For example, VANET, where we have vehicles. Then we also consider that UAVs cooperate with each other in that they can exchange their internal state, for example, their current trajectory, with their one-hop neighbors. And we also consider that they have collision avoidance capability. So what are the challenges in airborne networks? They are highly mobile, and as a result, it results in a frequent link breaks. Because of the link breaks, packets drop. So that's a bigger, we don't want that. And then whenever there's a link break, we need to reevaluate the routes. So there's frequent route selection, which results in high route switching cost. So basically, source has to retransmit all the packets on a new route. once a new route is selected. So it's a high route switching cost. So we want a routing scheme which can select a longer lasting route and can also proactively switch to a new route in order to prevent the packet drop. Another challenge is they are highly dense, and since there are a lot of nodes, they interfere with each other. This causes packet collision and increases the congestion in the network. In addition to that, since there are a lot of nodes, a source destination pair can have multiple options for route select, like multiple possible routes. So computing the routes every time, like frequently, it's high. It causes high computational cost. So we want, this requires a congestion-aware route selection scheme with low computational complexity. The airborne networks can also have dynamic mission requirements. For example, there can be new source destination pairs. So we want to avoid using hotspot nodes. A hotspot node is basically a node which serves more than one flow. So in this case, it's serving two flows. So we want to avoid hotspot nodes so that the congestion can be reduced. Then there can be different types of traffic. So different traffic types have different priority, they have different reliability requirements and different latency requirements. So the network has to take care of all these things. Then there can be nodes which may require packet transmission over multiple paths. So in this case, source one is using two different routes. One is this one and one is this. And how to select those multiple routes and that to dynamically and in a distributed manner. There is no centralized node to supervise this, this process. So this requires an adaptive quality of service aware route selection scheme. So what can be potential solutions? So basically we want to maximize the throughput and minimize the link delay. And there can be a lot of different factors which can influence these two performance matrices. So we want to have adaptive channel access mechanism where we can reduce the intraflow and interflow interference. The routing scheme should be robust and reliable so that it can avoid interference, it can reduce congestion, it can satisfy different types of traffic requirements, it can reduce the queuing delay, and so on, so that the throughput can be maximized and link delay can be minimized. So this together requires an adaptive cross-layer protocol design. So cross-layer means like designing some new features for MAC and some new features for routing and clubbing them, having the compatibility between them. So our protocol design objective is to facilitate a robust and reliable quality of service aware communication in airborne networks, such as UAV swarm. And for that, we propose to design adaptive, distributed, cross-layer QoS-Aware routing and MAC protocols. So in past, as Professor also mentioned, we have already designed a MAC protocol for directional communication. And I have already, like a part of it, I have talked about parts of it in Access 2019. So in this talk, I'll skip this, the details of this first, and I'll move to our work in progress, which is to design an adaptive routing protocol for dense airborne networks, where currently I'm focusing on robust and congestion aware route selection. So the existing routing protocols can be divided into three different types. The first one is geographic routing protocol. One example is aeronautical routing protocol. In this class, each node requires the GPS locations of itself, its one-hop neighbors, and destination node. Now, airborne networks are mobile and they are distributed. So a source node cannot find the real-time location of its destination node. Therefore, these kind of protocols are not suitable for mobile and decentralized networks. The second type is reactive routing protocol, such as ad hoc on-demand distance vector, AODV. So these protocols find a route when there is a need. So whenever there is a new flow generated, the source node will inquire the network and then it will find the route. This results in a discovery delay, initial discovery delay. And since the airborne networks have the tendency of frequent route breaks, this results in a high route rediscovery overhead and delay. So we don't want that because it causes a lot of latency and delay. The third type is proactive routing protocol, such as optimized link state routing protocol. These protocols are table driven, which means a source node already has a route in its table for the destination. So a source node can immediately find a suitable route to its destination whenever needed. As a result, there is no delay in route discovery. However, to maintain the table, there is a large signaling traffic overhead, and that increases as the density in the network increases. So our objective is to design a proactive routing protocol, since they can find the routes without any delay. And in particular, we want to design an adaptive OLSR protocol, which can compute long-lasting routes, stable, and congestion-aware routes. And in doing so, we want to reduce the computational overhead, while we also want to reduce the control overhead. So in this slide, I'll quickly go over the basics of the standard OLSR. It uses two main types of control packets, which are hello and TC, topology control. Hello packets are used in neighbor sensing for one-hop neighbor sensing, basically, and they are transmitted periodically after hello intervals. TC packets are used to disseminate neighbor information in the entire network, and they are transmitted periodically after TC intervals. And in standard OLSR, each node computes a shortest hop route for each destination node in the network using the digester algorithm whenever it receives a control packet. So it causes huge computational overhead, because it is computing the routes for all the destination nodes whenever it receives a control packet. So now I'll talk about our proposed scheme. So unlike OLSR or some other related schemes, we have used hop count, route lifetime, buffer occupancy, and link capacity in order to select a route. Here, hop count is basically the route length, and as the hop count increases, the packet delivery ratio decreases. So here, packet delivery ratio is the number of packets received at the destination divided by the total packets generated by the source. The route lifetime is the duration for which a route exists, and we want to have long-lasting routes because it reduces the route switching cost. The buffer occupancy is the number of packets in the queue of a node, and high buffer occupancy results in high queuing delay, which basically reduces the PDR, especially in the low latency applications. And the final one is link capacity, which is maximum number of packets that can be serviced by a node per second. And it is a function of channel capacity, packet size, channel utilization factor, and link quality. So first I'll talk about the link lifetime computation, which is needed for route lifetime computation. So what is link lifetime? So in OLSR, every node is transmitting the hello packet after hello interval, right? So in our scheme, each node includes its trajectory information in the hello packet, and the time when two nodes exchange their hello packet for the first time, that we are calling link establishment time, and the time when UAV pair moves out of each other's transmission range, that is the link termination time. And the difference of these two is link lifetime. So we want to basically find the link lifetime at the time of link establishment time in order to select a route. So UAV pairs, there can be different scenarios for UAVs. They can both fly in a curve, they both can fly in a straight direction, and one in a curve and one in straight direction. So for each different scenario, we can have a mathematical equation where so basically this equation is for when UAV 1 is flying in counterclockwise direction. This is UAV 1, and this UAV is flying in a clockwise direction. So at the time of link establishment time, how long will they be in range, provided they follow the current trajectory. So like that, we can compute for other scenarios also. Now, in the real scenario, the nodes will not follow the current trajectory, right? They'll change their trajectories, and that too randomly. So since UAV cannot change can change its trajectory unexpectedly, LLT of a pair cannot be computed based on the current trajectories alone. So in this example, on the right side, the link lifetime computed at the link establishment time will not be correct because the nodes have changed their trajectory. For example, here, then here, and so on. So we are recomputing the link lifetime whenever there's any change. Any of the UAV of the UAV pair changes its trajectory. And then the route lifetime is computed as the minimum of the link lifetime for all the links along the route. Now, how long should a route be used? A route should be used only for route lifetime duration minus time to live. So time to live is basically the duration, the maximum duration a packet can be in the network, because after that duration, the packet is useless. This is like basically, if you are watching a video, a packet should come within certain latency requirements. If it comes after, like, for example, 10 minutes, it's of no use, right? So this is what TTL is. So we want to select a route such that the last packet transmitted on the route should not be dropped due to the link break. And then we want to switch to a new route whenever any UAV of the UAV pair changes its current trajectory before the route duration. So that means we want to reevaluate at first trajectory change, at second trajectory change, and so on. Otherwise, after the route duration. So in this case, here, after the link termination time. So this is just a brief overview of route selection scheme. So we are using the breadth first search to compute the candidate routes, and the cost of each route is computed using this formula. Here, this is normalized hop count. This is normalized route lifetime. This is normalized buffer occupancy. So these metrics have non-linear impact of the route on the route cost, and in addition to that, they also interact with each other. So therefore, there is no closed form formula involving these metrics to compute the route cost. So so for the start, we took the weighted sum of the normalized values, and once we compute the route cost for each route, we select the route with the minimum cost. So as a result, this slide shows the comparison between existing OLSR-based schemes and our proposed schemes. So in existing schemes, the routing table computation processes, each node uses Dijkstra algorithm to compute route for all other nodes. Okay. Whereas in our scheme, we are only intermediate nodes use BFS algorithm to compute route to the source and destination nodes of a flow. So this significantly reduces the computational complexity, and the frequency is also reduced. In existing schemes, the route table is reconstructed whenever a control message arrives, whereas because of the route duration, we can recompute routes only after the route duration. The time complexity is for Dijkstra algorithm, it is E log times E log V, whereas for BFS it's E plus V. So the results. So we compared our scheme, and the simulation parameters used are we used 13 fixed-wing UAVs, which were moving at 20 meters per second in a 8 by 8 kilometer square area, and we generated data for 75 seconds, and we ran it for 10 different runs, and the results are shown for each of them, and the average results are also shown in the next slide. Here we consider Frisk propagation loss model, and one source destination pair is randomly selected for each run. So right now we are just considering one flow per simulation. So in this table, we are showing the PDR performance comparison between OLSR and our scheme. So we tried with different weight combinations. Here we are showing 4 such combinations, and on average, our scheme is giving like almost 20% improvement as compared to the standard OLSR. However, we observed that the one weight combination is not does not cover all the possible runs, all the possible scenarios. So each run basically corresponds to a different network scenario. So in some scenarios, not considering route lifetime gives a better performance. And in some scenarios, not considering buffer occupancy gives a better performance. So how can we have the best performance in each scenario? Or if I can rephrase that sentence, how can we adaptively change the weights? So most of the existing schemes, they have either fixed weight values, or they just simply try to find the next best next hop, so that the total delay can be reduced. But they nobody has so far seen it, like how to adaptively change the weights on the fly, and that too each node can do it independently of other nodes. So just to verify that each source destination pair requires a different weight combination, we tried using Bayesian optimization, where we took one source destination pair and said we use Bayesian optimization to compute the best the next weight combination, and then use that weight combination for the entire simulation duration, and then find the PDR. So here on the left side, we have shown the confidence interval after 20 iterations. So there's a lot of uncertainty here. And as the number of iterations increase, the uncertainty reduces. And if you can see, after 100 iterations, the samples are taken from this area. So it already explored all this part of the area, and now it's exploring this area. And eventually, once the Bayesian optimization, we ran it for a long, around 200 or 300 iterations, and then the weight it gave for that source destination pair was completely different than the 4 different weight combinations that we showed on this slide. So it means each source destination pair requires its own independent weight. I mean, or each source destination pair is a different story in our so it needs a different weight combination. So we cannot do, find the weight combination for each source destination pair, because that varies with the network topology, or there can be some other constraints. So how to go about it? So yeah, so importance of a metric depends on several factors, such as network topology, the TTL constraint, and number of flows, etc. Moreover, it varies with time. So that's even if we can find a weight combination, we cannot use it for the entire simulation duration, because it changes with time. So now our goal is to adjust the importance of each routing metric dynamically on the fly. And for that, right now we are using the learn to rank algorithm. So what is learn to rank? So whenever you do Google search, it lists a lot of options, right? So those options are listed in terms of the quality of the option. So for example, the first 2 options here, they just not talk about the Computational Science Research Center. They also give you when is the next Colloquium, and the third one gives you the link for Facebook and all. So it basically what's happening behind the scene is it takes a lot of documents as input. The indexer indexes them and then retrieves top K retrieval, and then there's a ranking model which basically ranks them, and then the document with the highest quality is shown on the top, and so on. So we are using a similar approach. Here, route is our document, and we want to compare 2 different routes and find which route is the best. So it can we can simplify it as a binary classification problem, and for that we are using logistic regression. So in logistic regression, each route we are collecting 3 statistics right now for each route, which are hop count, route lifetime, and buffer occupancy. And then a sample is created where the statistics of route R and route R dash are combined. And we are saying that if the PDR of route R is greater than the PDR of route R dash, then it has a better quality. So the output label should be 1, otherwise 0. And for that, we trained a model, assuming that the route with the better quality corresponds to the high PDR. So I'm still in the process of generating more data sets, more results for this. But right now, for around 1,200 samples, we compared our scheme with the heuristic model, and we observed that the basic, without like doing anything else, the logistic regression gives around 72% accuracy. So what does it mean? It means it is like able to compare two different routes based on their quality, and it's 72% time, it has an accuracy of 72%, which is significantly higher than the currently being used heuristic model. So once we have more samples and for more flows, right now, remember, we have just one flow. So more samples for more different flows, and then for different data sets, we are in the we will train up logistic regression for more samples, basically on a more bigger data set, more diverse data set. So the next steps include the comparison of the candidate routes based on the route quality and sort them in order to obtain the rank of each route. So if you see, it automatically adjusts the importance of each routing metric based on the network conditions, because all of your candidate routes are like the node, when the node constructs its candidate routes, it already have this network conditions like imbibed into it implicitly. So this importance, instead of like giving weights to each routing metric, it finds the quality of route, and based on that, it selects a route. So the automatic adjustment is already taken care. The next thing we can do with this approach is, remember, OLSR finds it has a huge control overhead because each node is generating the control packets periodically, whether it is hello interval or TC interval. So this is a huge control overhead. So what we can do, a source is interested only in certain routes, right? It does not need information of all the nodes in the network. So based on the ranks, a source can find out k best routes and can ask them to can select those routes, and then it asks the intermediate nodes on those routes to send their information. So instead of asking all the nodes in the network to send their information, only a selected few will send their information. So this reduces control overhead. More importantly, if you are not transmitting the control information, the channel is free. So it can be used for data communication. So this improves the channel utilization, which in turn improves the packet delivery ratio. So in future, once this work is done, I'll move towards interference-aware multi-path OLSR protocol. So existing work, they consider only node disjoint routes. So what is node disjoint route? In this example, route 1, route 2, and route 3, they all are node disjoint because they do not share any common intermediate node. However, the node disjoint routes are not necessarily interference-free routes. So for example, if source decides to transmit over route 1 and route 2, the transmission at node D can interfere with transmissions at node I and J. So it increases the congestion and therefore reduces the channel utilization, and therefore the packet delivery ratio goes down. So rather than having route 1 and route 2, we want to have route 1 and route 3, which are also node disjoint, but in addition to that, they are interference free, meaning that the transmission of any intermediate node on route 1 will not interfere with the transmission of any intermediate node on route 3. So that will be my first next step. And the second work is we want to modify the OLSR protocol for directional communication. So in the first phase, we have already developed the directional MAC protocol. So we want to club the MAC and OLSR and make sure they are compatible, and then bring in some new features, because with directional communication, with directional communication, a node will not transmit omnidirectionally, basically, right? So this communication can happen at the same time. The communication between I and J can also happen. So this brings some new features. So yeah, so I'll be clubbing the directional map along with the OLSR. So I think that was, I ran over some of the slides, but this is the end of my presentation, and I can take some questions now. And thank you for your time.
Thank you, Shivam. Any questions from audience?
May I ask one?
Sure.
Okay, in slide number 42, please.
Sure.
Do you know in advance the range of interference?
So yeah, so the range of interference is determined basically by the transmission range. Most of the time, it's like 2 times of the transmission range, and each node knows the transmission range.
Okay, but it's not fixed.
In our communication, since we are assuming it's fixed, but because each UAV will have like the antenna that we feed, and
Okay.
we are assuming that the antennas have the same features. But in case they are not fixed, that's a good point. In case there's like propagation loss or some other characteristic, we can look into that situation also, where the transmission ranges are not constant. So yeah, so that can be one more variation in future.
Thanks.
Yeah, it will actually depend on the power control.
Yeah.
So you can still assume, I believe, you can assume the maximum transmission range, and that you can use for, interference avoidance.
Yes.
Any other question from students or audience?
I hope it wasn't too technical.
No, it was not, certainly. So Shivam, you are mentioning that you will do it for multiple flows. So how that will change, the optimization as compared to single flow? So what additional challenges or impact that will have? You can go to that slide and talk about it, where you are showing the metric. Use this.
Yeah. So So in this case, when we have multiple flows, the first thing is we want to avoid using the hotspot nodes, because it reduces the link capacity. And at the same time, it also increases the queuing delay, because packets are stored in the FIFO fashion, first in, first out. And so yeah, so it can serve one flow at a time, especially when we are using omnidirectional communication. So we want to avoid using such hotspot nodes. And then it's not just so the similar situation, like it's not just about finding a route which is congestion, which is not disjoint. It's also about finding routes which are interference free. So so we need to find routes for each of those flows such that their communication cannot interfere with each other. So it's not just about finding the hotspot nodes, it's about finding the interference-free one-hop neighborhood from which the packet will traverse. So that brings more challenges, because on the fly, since the nodes are changing their locations, and that too independently, it's very tough to find when will a node become congested because of the hotspot nature, or when will it come in the neighborhood of another flow. So that's challenging.
Okay, good, yeah. Any other question from students? Some of you are from mathematics, about optimization, machine learning he's using.
Professor, I have a question.
Sure.
Hi, it's been a long time. Actually, I had a question about this slide. You mentioned that you'll be changing the route based on interference. Will you also be incorporating the levels of interference, or will you have a threshold before you change routes for interference?
Yeah, that's a good question, because So we can definitely use a threshold to decide when to change a route. Right now, how much interference? So right now, what we are assuming, if the packet that we have received, if it is above a certain ratio, and the receiver node can easily like decode it, it means there is no packet error rate, or there's no corrupted bit. So that's okay. So as long as the interference level is below that, we don't want to change the route. But once it goes above a certain threshold, after which the packet cannot be decoded successfully, that's a problem for the node. So it should change the route. Yeah.
Yeah, even with packet error rates, right? You want to have a certain high level of threshold before you change. Small packet error rates are okay.
Yeah, yeah. So that's like that depends on the physical layer. So right now we are assuming whatever the packet error rate is, it's constant. And yeah, so I'm not playing with that feature right now, but in future we can look into it. Thank you.
Good question, Nandini. Any other question? All right, if no more questions, then let's, Dr. Castillo, do you have any comments or any announcements to make?
I just want to thank you everybody for coming and have a great weekend.
Thank you. And thank you, Shivam.
And thank you, Shivam. That was a very nice. I actually understood most of it. So.
Okay. Oh, that's great. Thank you, sir.
Thank you.
I hope to have more next time.
All right, everybody. Thank you, everybody. Thank you, Shivam, and thank you, Dr. Castillo. Okay, bye.
Bye.
Bye.